So next week, you're going to read chapter 6 and chapter 7. It's interior and exterior finishes, or exterior and interior finishes. I forget which one comes first. But we'll go through building services and that sort of thing. It's the natural juncture after we cover today, because we talk about the frame system today, and then we move into kind of the services of a house. Today we're speaking mostly in terms of residential. There are some multifamily buildings, some larger scale, that are built in a very similar manner, up to 3 or 4 stories. The book pretty much exclusively talks about just residential, so it's really good that we have the models from the Construction 135 class, not to be confused with my Architecture 135 class, separate classes. But the Construction 135 class makes these models. It's offered in the fall at night and in the spring during the day. It's the opposite of this class. This is offered at night in the spring and fall during the day in the fall. So luckily they have a whole bunch of these left over so that we can point out. There are occasionally mistakes on them, but for the most part it's good to have it sitting in front of you. When I talk about the slides today, it's helpful if you actually look at the model in front of you because you see it kind of in three-dimensional form. A lot of the drawings that I have been flattened out, so they're harder to see, which is why I like to include all the models as part of the lecture. Okay. Maybe. So let's start with a brief history of wood frame construction, why it got here. This is considered to be the first, quote, American building method. It was developed in America, and it's now spread throughout the world. But basically our philosophy on this was that a whole bunch of small elements can hold the same amount of weight as a large element. And so we can use this repetition to support the same amount of weight at a relatively cheaper cost, right? This was made possible by a water-powered sawmill, so we could easily cut smaller dimension lumber, right? And machine-made nails, right? It used to be when you had to hand-make nails that nails were extremely expensive. As soon as we started to be able to produce them in mass, the price went down. Unfortunately, the price of nails seems absurd now, but whatever. That's a side note. So the earliest types of frames that we started to see were what were called balloon framing systems. And they were constructed exclusively of slender, closely spaced elements, right? The kinds of things that we're seeing in your buildings, though most of these are platform framed. And there's a few problems with that, which we'll talk about in a little bit. These closely spaced members, right, depending on where they are in the building, if they're on the floor, right, they're going to be called joists. Right? But it's the same thing. If they're on a wall, they're going to be called studs, and if they're on a roof, they're going to be called rafters. It's the exact same thing. It's the similar pieces that are laid out, and you can see these really easily, right, on any one of these. Well, that one has a solid floor, but most of these have plexiglass floors, rather dusty, right? But you can see the joists in the floor, the repetition of members, right? You guys can all see those. On the walls, we have the repetition of the studs, right? And on the roof, we have the repetition of the rafters. The same thing on each surface. And it's just a matter of memorizing that terminology to start to understand what these are. Okay? So what we got away with were the big, heavy posts that we talked about last week. Right? And the need for expensive joints, a lot of people to work on a particular building. One carpenter, one single person can carry any member that's on one of these construction sites. A little bit less true if you're doing, large 2-story, big open spans. You've got a big beam that's mixed in. It might be a little hard to carry it by yourself, but the general philosophy is that any person on the site could carry any one of the elements. There's no expensive joinery anymore. We're just substituting in nails, very inexpensive, right? So that's a good thing. So this kind of sums it up. A man and a boy can now attain the same results with ease that 20 men could do in an old-fashioned frame. And by old-fashioned frame, they're talking about heavy timber that we talked about last week. The balloon frame can be put up for 40% less money than the mortise and tenon frame, right? And so this is in 1865. So you can see that it's really an economic decision to switch to this rather than an aesthetic decision, right? We're going for economics here. So in balloon frame, right, we have full-length studs, right? So remember, studs are the repetitive wall elements. We have full-length studs that run all the way from the foundation through the second floor up to the roof, right, up to the rafters. So it's one continuous piece. And so most of these buildings don't have that. The closest we have here is in this two-story, kind of on the outside here, right? Those are running almost 2 stories, 1.5 stories, right? So it's kind of a bit of a hybrid in there. But it's not very common today. One of the big disadvantages is if this was just framed up with long, skinny pieces, right? If there was a fire in here, right, and we're able to get into the wall cavity, right, it could shoot up through this cavity like a chimney and into the second floor. Right? Does that make sense? Right? Because we have an open wall cavity, fire gets in, goes up, right, and can come out into the second floor. So we have to install these fire blocks right here, and you'll see it in every one of the balloon-framed buildings. There'll be a fire block right here that separates the bottom story from the top story, so that doesn't act like a chimney, right, and cause the fire to jump up into the second floor, right? So that was our solution for it, right? The big problem with that is also that you have to have tall, straight members that are tall enough to do that spanning, right? And with the way lumber is today, right, we're better off with shorter, smaller pieces, right? So we started to do something slightly different, which is called the platform frame system. And it works a little bit easier because you're not dealing with such long pieces. It's a little bit quicker to put together. So the platform frame is really the standard building method, though balloon frame is still used occasionally, and it may be used in combination. So on one project that I did, it was a barn, nothing particularly exciting, right? But we had walls on either end that were rather complicated with the big openings and what have you. We decided to frame those actually as balloon frames, so they have continuous studs. The side walls, right, were framed as a platform, so we kind of hybridized the system a little bit. That happens. Certainly on something like this, it's a bit of a hybrid system because you have some sections that's actually spanning the 2 floors, and you wouldn't want to have a platform, right, without a floor attached to it. So you wouldn't divide this and put a platform in here. It wouldn't make any sense. You want these to continue to run through. So it's not to say it's exclusively platform, but it's easier with platform frame, right? And so the general philosophy about a platform frame is that we're going to start with a floor platform, and we're going to build that platform, right? And so we'll start with the base of the house. Obviously, this is foundation with crawl space. You've seen something like this before, right? And we build this platform right on top of the foundation. We put down our plywood, and we're going to go through these things. The way the book organizes this chapter is it's like gives you a little bit of an overview, then it goes into a little bit more depth, and then it goes into even more depth. So we end up going through these things several times. So we'll come back to the platform and how it's put together, right? After that, we build our load-bearing walls, usually flat on the floor, and tip them up into space, right? And so we put those load-bearing walls in position here. We brace them temporarily. And after we get those in, we move to the second floor platform. And we frame out the second floor platform. We put our plywood down, right, on top of that as our decking. And then we continue to work our way up with the next set of load-bearing walls, right? And then finally we end up with the roof on it, right? So that's how platform frame. And you could just think of platform, and basically the roof is a platform, right? It's not something that you occupy, but it's the same kind of thing. Okay? So advantages or disadvantages of a platform frame, right? It uses easy-to-handle lengths of lumber, right? An 8-foot 2x4 is a lot easier to deal with, right, than, say, a 20-foot 2x4, right? And so it's much easier to work with, so therefore it's easier to get around the site, if I can talk. Vertical hollow spaces are automatically fire stopped because you have that second floor platform, right? There's no way for the fire to get from the first floor to the second floor. That's good. And the platforms are really convenient work surfaces to be able to build your walls, right? If we're building the first set of walls, we have a nice flat surface. We can lay out all our studs. We can put them together and tip them up into place. Build our second floor platform, do the same thing again, right? So we have a nice work surface to actually build with, which is a big advantage, right? The big disadvantage of platform frame is that on each of these we have a thick wood layer with the grain running in the opposite direction, right? So you guys remember back to chapter 3 before spring break. I know that seems like ages ago, right? We talked about wood, right, and the fact that wood shrinks when we take the moisture out. It doesn't shrink much at all, right, in the long direction. So if we had a stud that was standing here, right, it wouldn't shrink much in this direction. So that's consistent. But if we turn it sideways, it's going to shrink a fair amount, right? That would be radial shrinkage, okay? So if we have a large horizontal band, right, say something like this that runs all the way through the building, right, this is going to shrink more than something on the other side. This is probably the best example, right? This horizontal band here is going to shrink. This piece isn't going to shrink. So we have this disjunct where this part of the building is going to shrink, this part isn't, and we have to be able to deal with that in our siding and accommodate that, right? It's not a huge amount, but it's something that we want to be aware of. Likewise, even if you just have a simple building with a simple second floor that is the whole size of the building, right, that band is still going to shrink. So however you put your siding on, you have to leave a little bit of extra space so that when it shrinks, it's going to be able to be accommodated, right? And you'll see that depending on whatever the siding system. And we'll talk about exterior finishes next week. But no matter what siding system you're using, whether it's stucco, right, whether it's wood, whatever, you're always going to see some kind of a little transition band between those two floors to accommodate that shrinkage, right? So usually a platform frame is made of nominal 2-inch members, right, which means they're actually 1.5 inches, right? What's a 2x4? 1.5 by 3.5. How about a 2x6? Okay. How about a 2x8? 7.25. 7.25. Right? It goes to 3/4. After you get to that 8, it goes to 3/4. It's delivered to the site in the nearest 2-foot increment. Right? So you're going to get your studs. You're going to get 10s. You're going to get 12s, etc. Right? And a stud actually isn't 8 feet because you accommodate the top and the bottom plate, but that's a little bit too much detail for you, right? It's cut to the precise size on the job site itself, right? So it's delivered in bulk, and then whoever's responsible, the general contractor who's putting this building together, is going to determine how to maximize the yield out of whatever the pieces are that they have, right? And that's exactly what a class like 135 would be teaching you in terms of how to actually build the building itself, right? So each plane of the structure is made by aligning all of those parallel members, right, at specified increments. They're usually going to be 16 inches on center, which we'll talk about in a little bit. Sometimes they're 24 inches on center, right? After we lay it out, we'll nail some kind of cross pieces to it, right? We might nail, this might be something that's temporary. We might go ahead and put some of the shear on it. In California, we're going to shear almost the whole building anyway for added seismic stability. So depending on how you're actually building and where you're building, that's going to vary a little bit. But the idea is to stabilize the frame so that it's relatively stable. And then you're going to tip it up into its position, right? So covering it with sheathing, right? And that's going to basically solidify that either platform, wall segment, or roof segment into, it's technically the sheathing is called a diaphragm, right? It ties everything together, and it makes it one structural unit rather than a bunch of individual pieces. That's part of what unifies it, right? So think stable structural unit, right? Here's our subfloor, for example. There's all our joists, right? We're unifying that whole platform together with the sheathing, with this plywood subfloor. Okay? So in terms of thinking about the basic balloon or the basic frame, platform frame diagram here, right? We have our parallel spaced members that are in the floor, which are called joists. Good, right? Some of you are like, this is total snooze. Yeah, I know what I'm doing, right? But remember, there's a lot of people who haven't heard this stuff before, right? Then we have our parallel members that are here in a wall. They're called? Excellent. I'm hearing much more confidence there. That's good, right? Parallel space in the roof? Rafters. Nice. Okay? So we're going to get you memorizing these things, right? So yet another slide. Do you think this is going to show up on a test? Yeah, probably, right? Okay? So parallel pieces are called floor joists, cross pieces, right? And we're going to go through this again in diagram form. What they're talking about cross pieces are things that, so let's look. You guys will have to look on the second floor a little bit. There's no openings in that. This is probably I keep going back to this one, so you guys are lucky, right? So this one has a little bit of an opening, right? We have our series of parallel joists, right, that are running on this floor. The piece that runs around the outside, right, is called a rim joist. And we'll come back to this. We'll say it again. We'll show you more drawings, right? This is not the last time I'm going to talk about it, right? If there's an interior cutout, like for this set of stairs, those are generally called headers, right? just like a header would be an opening for a door. So if it's an opening, it's usually a header. Band joist is just another term. The other thing that you will find, especially those of you who have done light wood construction before, you'll notice that terminology changes a little bit. There are things that we call certain things depending if they're more slang terms, they're more formal terms. I go by whatever the book says, but if there are other things, like the best example would be a mud sill, right? A lot of us would call it a mud sill. I will have a terrible time switching. The book calls it a sill plate. So there's just going to be a few of those terms that are going to float around, right? If on a test you said mud sill and the correct answer is sill plate, I'll still give you mud sill, right? Anyway, you guys don't even know what that is. Don't worry about it. We're going to get to it, right? So the sheathing in that sense is called the subfloor. So if we look at the actual diagram here, this will help show you, right? That's why I'm referring to the physical models. We're referring to the diagrams. We're going to go back and forth all night, right? In something like this, we have all our parallel pieces, which are called the joists, right? Around the outside, tying this whole thing together is what's called the rim joist, right? It's the rim. It's like the rim of a bowl or something, right? The rim joist, right? Inside here, right, these pieces are called headers, right? That's heading off the opening for the stairs, right, because these don't go through it. Then we have our subfloor that's going on. Notice that the subfloor is perpendicular to the direction of the joist, right? We'll talk about that in a little bit as well, right? So if we go into wall structure, right, and this is what I was saying about the book repeats itself. So if you actually read your chapter, you realize this. Yeah. Sorry. It's a great question. I'm glad you noticed it. We'll talk about that a little bit later. This is what you're talking about right here, right? The short answer is that this is a cantilever that extends out beyond the foundation. So in order to accommodate that piece that's sticking out as a cantilever, we have to have these tie back into the structure of the building so that we can accommodate weight on the outside end, right? And we'll talk about why they're there and how you would actually do it a little bit later on, but that's the short answer. Okay, so parallel pieces are called the studs, right? The piece at the bottom of the wall, right, is called the sole plate, bottom plate. That's what I've always called it, but they call it a sole plate. And the cross piece at the top is called the top plate. Okay, so if we look at the walls, and we're working through the terminology slowly, right? If we look at the walls here, we have our repetitive elements, right, that are all our studs, right? On the bottom piece here, right, is what we're calling our sole plate, right? The easiest way to remember it is like the sole of your shoe, right, being on the ground. That's a sole plate. Bottom plate would work fine for me, right? And then up top, we have our top plates, right, which is why, to me, bottom plate seems to make sense. If you have top plates, you would have bottom plates, right? And then we've got all of our individual studs there as well. Make sense? So you guys all see it on your models, right? Right, where your sole plate would be, your studs, your top plate.
So the sole plate would be this whole.
It's this one that runs along there, right? So the acrylic would be your subfloor.
So what about
right?
like this up here?
So that would be a rim joist because that's the floor cavity, just like this would be a rim joist, right? Then we have our subfloor, then we'd have our sole plate, then we'd have our studs, and then it's actually a double top plate. We're going to talk about why you double that up a little bit down the road. Does that make sense for you guys? So you guys, when I go around individually, just bear with me, but it helps to make sure that everybody is clear and really understands, right? Sometimes, like I said, yeah. So think of this instead as a rim joist, right? That's the terminology I'd like to solidify, right? So if we come up here, we have a rim joist here, right? Then we have our bottom plate or our sole plate, right? Then we have our stud, maybe, coming up there, right? We have our top plates here. On top of the top plates for the next floor platform is our rim joist with all the rest of our joists, right? Then we go into our subfloor, which is the acrylic, right? And then we come up to our bottom plate, and we continue our way up. What is? No, this is different. We'll get to it when we get to a little bit more about roofing. I don't want to confuse you with too much, so just hang on, right? Do you guys feel okay? Yeah, okay. You guys all feeling okay? Yeah, makes sense? Likewise? Okay. Okay, so let's continue on. Right? So let's go back down to the ground. I deliberately left off roofs because they get a little bit more complicated. We'll come back to them in a little bit more detail as we go along further. So let's come back down to the ground and let's talk a little bit about foundations. And it doesn't really hurt us to re-talk about foundations. I'm actually putting some review questions in here, knowing that at some point the final is going to come, right? So it doesn't hurt to talk about foundations a little bit more. But these are much more in the scale of a residential foundation. We're not going to see the big caissons or anything in residential, right? So our foundation is typically going to be made from concrete or some kind of concrete masonry unit, right, or a combination of the two. Special attention must be made to insulate, damp-proof, and drain basement and foundations anytime it's habitable space. Again, we live in California. We have a lack of basements or underground spaces. They can exist, but it's not very common. If you were back east, almost everybody would have them, right? So in terms of laying out a foundation, right, and why they stick this in with this chapter, I don't really know. It seems like it would be appropriate with the foundations chapter, but whatever. I didn't write the book. So this is laying out a very simple foundation, right? We have to lay out the excavations, right? And what would seem logical is that you go out to the site, you do a little surveying, and you just spray paint on the ground where you want to cut, right? The problem is if you've ever actually done any excavation, you realize really quickly that if these were spray painted lines, right, they would be gone, and they would be covered with dirt, and you'd never see them again, right? And you'd lose complete track of wherever you were going to be. So what they do is they set up these things that are called batter boards, right, that are these little stakes, right? There's 3 little stakes with these little cross pieces on them, and they mark on them where to attach a string, right? And you attach a string on one end, you attach a string on the other end, and it goes across the 2 corners, right, where you want your excavation to happen, right? Likewise, you can lay it out for where your foundations would go and et cetera, but you get the idea, right? And so we have cross piece there, cross piece there. Right below that is where we want the corner of our excavation to be. The nice thing about that layout string is you can take it away while you're digging, right, and then put it back in. You put the tractor inside, you dig for a while, you can put the string up, that sort of thing. It's repetitive, but these batter boards are outside of the excavation, so that they're not going to get in the way and they can stay there during the construction process, right? And so if we look at it now, you see that the batter boards are nicely, right, outside of the excavation, but we've dug out where we need this to be, right? They dug out a little bit more just so you can see the bottom of the foundation, right, in the drawing, okay? And so these little colored dots are going to correspond to a couple slides down the road, right, just so that you can see where they would occur. These are straight out of the book, so you can reference, right, where they are. But you get the idea, right? This is our formwork. We have down at the bottom, we have our basic footing, right? On top of that, we have our wall. You guys remember back to the form ties and how we formed up the wall with those segments and we tied them across and we filled them with concrete with all the rebar. Has a key in the bottom. Kind of remember this stuff a little bit vaguely? Yeah. Okay. So we can see the formwork up here, right? We have our anchor bolts to tie down to the building, etc. Notice also here, this is good. There's a little drain pipe with some drain rock around it, which is good for drainage, right? We're going to make sure that we get as much of that water out of the foundation as we can. Okay, so let's go back and review. You guys remember this slide? Looks somewhat familiar, maybe, right? This is out of chapter 2, which was the second lecture we ever had, right? So go back a little bit. What are all of these things, right? So take a little bit of time, draw this out, try to figure out what they all are, right? And we'll come back and talk about it. It's a good start. So you guys also remember that, these are the kinds of things that when I show something with some fill-in-the-blank questions, they like to reappear down the road. So number 5 is pointing to this right here. Number 4 is pointing to whatever the membrane is that would be on the wall. pull that slide out. No, you don't get the answer now. Yeah. hmm That would probably work. But what will happen? Yeah, no, that's fine. On a test, right? If I were to, and I should address this to all of you. It's a good question. So Angela said, if something like this were to show up on a test, and I needed to fill in the blanks, and something like, let's use number 6 as an example, right? Number 6 technically is a perforated drain pipe, right? Is the full terminology for what it would be, okay? But if you wrote drain, that's what Angela was asking. If you just wrote drain, would I give it to you? Sure, of course I give it to you, right? But on a test like that, what I will do, and on the next test is going to be the final, is there'll be a page on the back of the test that will have every fill-in answer on it. It'll have a lot more than the fill-in answers that are actually on the test, right? There'll be a bunch of other words on it, but you won't have to come up with the spelling or something like that. You'll be able to look through the list, or you remember that it was you're trying to think of trimmer, for example, and you're like, I know it started with a T, and you'll look at the list and say, oh, there's a T. That's what it is. I remember, right? So I'm not asking you to memorize them so that you can come up with them out of the blue, right? But I want you to be familiar enough so that you would recognize the term, right? And so you wouldn't have to spell it correctly or any of that kind of stuff. Okay? So you guys ready to move on? Next slide. Okay, so let's talk through some of this, right? These little color pieces go back a couple slides, right, in terms of the locations for where they would be. So let's jump back a couple slides, right? So purple is this upper section, right? Green is the lower section down here at the bottom, I think. And blue is in the middle, although I'm thinking that my colors are off, so that really didn't help at all, right? These should be flipped, but whatever, right? The concept was good. Maybe next year I'll get it right. Whatever, right? So up top here, we didn't really talk about this too much in the foundation section yet, and we didn't talk about it because we didn't have anything for the foundations to attach to, right? Now that we're building a wood frame building on top of this, we need some way to attach the wood to the foundation, and it wouldn't make any sense for us to nail the wood to the foundation, right? Because the nails aren't going to hold in the concrete. So what we do is we embed something that's called an anchor bolt, right, into the concrete, and it has this little, I need a stick again. Excellent, right? It has this little L on the end, right, so that it's embedded into the concrete, it folds over, and if you were to pull up on it, right, it would be wedged into the concrete. You wouldn't be able to slide it out, right? And so the shape of it, sometimes these have a little U on them, sometimes they're an L. It varies based on how much strength they need to hold. In the state of California, we have a lot of requirements for seismic hold downs. So the book doesn't really go into them in that much detail, but it's sufficient to know that this is the basic, right, setup. And if you were doing something for seismic, it would be something far more substantial that would be tied into the reinforcing of the foundation. It would be a lot bigger, right? But this is kind of the basic idea. You need some place to actually attach it, right? These two little dots, which have been cut through, right, those are each rebar, right? Now, if this were in the state of California, we'd have a whole bunch more of those dots, right, that are actually here. But, we get the idea. We see a few more down here at the bottom, right? So up here we have backfill. Notice that the hatch switches slightly in direction. That tells us that this was where the excavation was and that this fill was put back in. That was backfill, right? So that's in there. Now, what do we know about this excavation? It's very cohesive soil. Good answer, right? Because it's a very steep excavation. If it were in sand, it would have to be tapered way back, right? So we know it's very cohesive soil. This is our original soil that's out here, right? Number 4, I told you, was pointing to the membrane that's on the wall, right, which is almost impossible to point to in a slide, right? I think when I ask this down the road, I might put a little note underneath that says this is pointing to the thing that's on the wall, not the wall itself, right? And so that's the waterproof membrane. Remember, we have to provide some waterproofing because the concrete by itself is porous to water. Water would end up coming through, right? Down here, it's a 2x4 keyway. If you just put keyway, that would be perfectly fine. That's the mechanical connection between the wall and the footing, right, to make sure that those two don't slide past one another. There is, of course, rebar that goes through that keyway as well, right? We have a perimeter drain or a perforated drain pipe, something like that, that's actually providing the drain, right? And all the way down here at the bottom, we have a footing. Okay, so that's good review of foundation stuff. The next couple slides, I'm not going to be as intense about, though they do talk about them in the book, so it's important to talk about it. If we had some kind of a basement that was a living space, and I apologize, this is a little blurry, right? But it's out of the book, so you can reference it. If this were a living space, in either instance, we would be very careful to make sure that that has some insulation attached to it. And there's a variety of ways of doing that. We can run rigid insulation down the outside of the building here, right? They're also putting batt insulation up above, right, where we have just the wall. It's the combination of the rigid insulation and the concrete that will provide that insulation. We could, right, run the insulation down and inside. This represents a furred out wall on the inside, which if you had a living space and you wanted sheetrock on a wall, right, not an open concrete wall of a typical basement, you would do that kind of furring out. Gives you a cavity. You can put the insulation in that way as well, right? Other examples for how you do the insulation, we've got some rigid insulation that's coming down here. If it's a particularly cold climate, you can actually pull the insulation out this way, and that will be as effective as continuing the insulation down, right? Has to do with how the cold transmits below a certain depth in the ground anyway, right? And so something like this, we're running the insulation down and across the floor, which I would never personally do. The book says that it's doable. I would be totally worried, especially if this is fiberglass, which is typically what this symbol would represent. If this ever got wet, you'd lose all the insulation value in it anyway. So I wouldn't really recommend that one. But the book shows it, so it's included, right? If it's a slab foundation, right, similar conditions here where we're pulling the insulation down to make sure that we're not transmitting heat and cold through the concrete itself, right? Another example here, it's an interior slab, but we have insulation here, and we're pouring this higher up than the outside wall, just a different strategy for the slab, okay? Okay, so in terms of planning the frame, right, how does this come into being, okay? The architect, right, or in a seismic state, heavy wind load state, the engineer, right, is going to determine the appropriate sizes and layout of the framing members, right? And so this is kind of an interesting sidebar that we'll go on for just a second. And that is the philosophy of an architect versus an engineer, right? And technically, as an architect, especially in the residential realm, right, you go to school, you get your degree, then you go on and do your internship, and eventually you pass the state exams. There's 7 tests that you have to pass, right? And you become a licensed architect. And with that, you get a stamp that says, I'm a licensed architect. And you can then do this kind of a layout, calculate the loads on individual members, right? Tell the contractor this is where all the beams go, and you can stamp the drawings to say this is certified. Engineer doesn't even have to look at them, okay? However, if you live in an area where there's a lot of seismic activity, right, or if you're doing a building larger than, say, a simple residence, right, chances are you're probably going to want to have an engineer look over them, right, and pay an engineer to consult because you really want their stamp on it and their liability on it rather than yours, right? And so it's this kind of interesting catch-22 about being an architect versus being an engineer or being a designer and using an engineer or what have you, right? So in the state of California, it's just important to notice that this engineer part is probably much more common than it would be somewhere else, right? If you're in the middle of the Midwest, less likely that you're going to need an actual engineer, right? And so they're going to lay out this framing members, right? And they're going to communicate this information to the general contractor, to the person who's responsible for building this building, right? And that's going to be through framing plans, right, and details, okay? Larger scale section details are going to show major connections in the building, right? Certain things that need to be done a certain way to make sure they're correct, right? And they can transmit the loads effectively, right? We're also going to show architectural floor plans that are going to show the location of the rooms, the sizes of the rooms, the location of interior walls, those sorts of things, right? Because basically from a set of plans, and this is what blueprint reading, how many people have taken the blueprint reading, the 114? Wasn't it, is it 114? I think so, right? So if you've taken that, you're familiar with that. If you're taking working drawings or you've done working drawings before, you're getting a better sense for what this is, right? When you're going to go build a building, you need a complete set of plans that really identifies where are all these pieces going to go and how am I supposed to actually build this building, right? And so that's if you're wondering more about this, a good strategy would be to take a 114, right, or a 244, a working drawings or a blueprint reading to give you a better sense for how this stuff goes together and what are the details, right? So the architectural plans are going to show the basic locations of room. So this would be an example of an architectural plan, right? And of course, I have to pick some kind of kooky example. I can't pick just the traditional example, right? In blueprint reading, I think you do like a simple brick residence, and then you end up in a Wendy's or something. So you go through a variety of those, which are technical and interesting in their own right. But we're going to show something a little bit more different. So we have a basic architectural floor plan, which is going to show us general information, right, about this building, where the locations are. Generally, it's going to give us a few more dimensions than something like this, right? This is a little bit more design schematic. We're going to have exterior elevations that are going to show the outside faces of the building, right, with vertical dimensions to show us how tall the building's going to be, where the various floor plates are going to be on that particular building. Those exterior elevations are typically going to show the types of siding, right, that are going to be used on a particular building. Is it going to have some rock work down at the bottom, right? Any of those kind of aesthetic details are going to be shown on an elevation as well, right? Then we're going to have building sections that are cut through, right, each one of these buildings. And basically, some of you already have a section, like that one in the back is basically a section because they cut half the building off, right? But it's a building section. Yours is cut half off too, right? It's a building section because we cut through it. And what that shows us is the relationships of various rooms, right, in the kind of space that we inhabit, right? It's the space that we walk around in. And those of you that have taken studios with me, right, or have heard me talk about this stuff before, I would argue that the section is actually the most important thing an architect can draw or understand, right? Way more important than a floor plan in terms of understanding how we appreciate space. So that's what building sections are drawn for, right? And so we end up with something like this. Well, that's really light. I think I have another. That's a darker image of it, right? So we have our basic building section that's showing us, right, what the finishes should be, what the building should look like. Obviously, it's going to have more measurements than this, but I wanted to show you a more interesting example, so we had to go a little bit different, right? Then we're going to have what are called interior elevations. And so sometimes these are more detailed, sometimes these are less detailed. It depends how much client involvement is really in this. So if a client is really interested in picking out exactly what their cabinets are and they're willing to just do it for themselves, that's fine, right? Sometimes an architect will go through all of the information and actually draw up these elevations. This is usually for a client who really needs to have a visual understanding of what the kitchen's going to look like, right? And so they'll draw up these kinds of kitchen interior elevations that show exactly the type of cabinets, exactly the placement of the cabinets, what are the cabinets, right? That sort of thing. So they're much more detailed. And so it's important to kind of realize that depending on who the client is, this may be too much detail, it may be not enough detail, right? They might need some kind of a 3D model to really see it as well, right? And so we end up with the actual house, right? And so this was the example that I wanted to show for this. Less than a traditional foundation, right? It's a floating house instead. So if we jump all the way back to those exterior elevations, right? These look a little different than foundations because these are actually flotations, right? So they're big tubes that are filled with air and or styrofoam that are going to support this house. And the house actually sits right in the mouth of this little creek that comes off. The rest of the lake is back over this way, right? And there's a nice little creek here. There's a second floor bridge that comes in from this side, and you obviously see the dock down a little bit lower that's accessing the opposite side, the opposite shore, right? And so this would be a little bit harder if it was an environment where the lake varied, right, or it was on the ocean where the tide varied, right? But in something like this, it's relatively stable. It's not too bad, right? And so this is what it looks like from the inside. So this is not your typical houseboat. This is actually a very, very nicely designed building. A couple things I do want to point out for those of you that are architecture people in here, just because I can't not talk about it, right? So a couple little details that they did, right? They left a little tiny slit right along the roof line there, right, so that they have a window right along there. That skylight is bringing light in and washing that whole upper wall, which really lightens the ceiling, right? And so these are the kinds of little tricks that you should pick up and study during your light studies, right, when you're doing your studio designs, because it can really make the difference in a building like this. It also helps a great deal to reduce the glare in looking out a building. So this is getting kind of technical. So if I'm going over your heads, I'm sorry I'm going off on a tangent, but this is fun, right? Well, it's fun for me. I don't know. Maybe it's not fun for you, right? So the other thing that's great about something like this, right, is because we're lightening up this wall and it's brighter, right, when you look out this wall, you don't squint because there's not going to be as much of a difference in the light condition from inside to outside, right? And so you won't have to focus between the two. You'll have this, and if you're looking up here and you scan your eyes down and look out the windows, there isn't a big adjustment that your eyes have to make, and it's much more comfortable building to be in, right? So that's why lighting's important and why you study lighting conditions and what have you, right? Another example here, right? There is a nice house that's actually attached, to the ground and to utilities and that sort of thing, right? So it's a little bit easier, but this gives you a really good sense for the fact that this is really actually floating out on the water. I'm betting money that the utilities come in through that bridge. I've never been there. I believe it's up in Canada, but I've never personally been there, so I can't tell you where the utilities came from. Okay? So back to the more mundane stuff, right, because we have to cover that as well. Okay? So this would be an example of a framing plan, right, for the ground floor platform. Right? So this is the kind of thing that if you were in blueprint reading, you saw some of these. Right? And depending on the style of the architect and the way they've chosen to draw it, it's going to vary a little bit, but this is relatively generic, right? And so it helps us kind of understand, right, as a contractor. So this would be something that the architect or the engineer would hand us, and then us as a contractor would come in and say, okay, I understand how I'm supposed to frame out this space, right? I understand that there is going to be a stair opening here, right? I understand that my joists are designed to run this way, right? Depending on the length of the span from the exterior wall across, right? Chances are, if this is long enough, we have no dimensions on this, so we don't really know how far it is. Right? Underneath here, there's a beam. Right? We'll talk about what that beam condition would be and what it would look like. So we've got a span that's going from here, the outside wall, to the beam, and another span that's going from the beam back over to here. Right? And so we have some kind of a support that's in the middle. Right? At special locations, this is a fireplace opening, stair opening. Notice these are a little bit thicker. Right? Usually means that we've doubled up two joists together, and they're working together instead of just a single joist. We've also headed off this stair opening, right? So there's a little header. These little kind of tapered lines are indicating that there's some kind of a joist hanger, right? Some kind of a piece of hardware. We used to have some up on a board somewhere. We've got hold downs in the back, right? We don't really have. It must have disappeared. I feel like it used to be over there somewhere, but oh well. Stuff moves around, right? It's a joist hanger. We'll show pictures of that later, right? That's attached to this horizontal piece that allows us to attach each of the joists to it, right? Just like Paula pointed out earlier, right? This set of joists, right, is running in the opposite direction because it's supporting a cantilever that goes beyond the outside wall, right? Typically, the rule for cantilever is that the cantilever can't extend more than a third, so you need 2/3 back to 1/3 that extends out. Usually we can be more conservative than that. Sometimes it can be less if you have a really creative engineer that's willing to do some crazy things, right? I was on one project where they had to do a cantilever that they didn't have enough room to tie these back as far. It was not my project. It just happened to be a site that I was on. I think it was a 1-to-1 ratio, so they couldn't tie it back as far. And the engineer actually specified the hold downs or the joist hangers to go upside down, right? So that you had that extra tie-down support, which would tie further back into the building, right? So there's creative ways around it, but you get the idea, right? And this is much more conservative. Notice we have a doubled-up header here, right? And then all of these pieces are going to extend out to be able to support that cantilever. Okay? So if we look at it in 3 dimensions, right? This is the same floor that we were just talking about, right? I believe they have a steel beam. It's a bit hard to see in this slide that runs underneath right there. We have our joists that are running across, right? Here it's easy because they're running across to meet the steel beam, right? Across here, they're reaching that header, so there'll be little joist hangers there, right? These would run across the rest on the beam, and then there'd be another set that rests further along. Notice we have all our plywood sheathing that's on top of the floor running perpendicular to the direction of the joist. Right? It's always going to be the long direction perpendicular. Right? So, just like before, maybe this time I got the colors right. Right? We have some color coding stuff. A is going to happen here on this corner. C is going to happen here. And this blue dot here is going to be at that cantilever, so you'll see a little bit more detail on the cantilever in a second. Right? So at A, this edge detail, remember, depending on what side of the building we're on, right, the joists are going to meet that outside of the foundation in a different manner. Right? And so in this particular instance, right, we have the joist running this way, right, parallel this way, and we need some way for it to rest on, right, the outside joist. So this would be the rim joist. These would just be the floor joists. And that rim joist is resting directly on what I would call the mud sill, right, but what's called in the book the sill plate, in contrast to the sole plate, right? So there's two different ones. This would be the sill plate, which we're going to talk about more in depth later on, right? So that joist is going to rest directly on the sill plate. On top of that, we have our plywood subfloor, right? Here, right, this is the cantilever joist detail, right? So our cantilever joist is going to extend, right? There's our sill plate, our mud sill, right? Cantilever joist break line is here. It would go back further over here. It extends out past, rests on this, but extends out past this, right? And the rim joist is way out here floating in space, okay? Likewise, if we had this going all the way, we don't really want little critters and whatever to be able to climb up and over and into our basement, right? So we're going to put some blocking right here, right? And this is a little bit of the way we draw things, but if you ever see a box like this that has a single line across it, that means it's blocking, non-structural blocking. And so if you take blueprint reading, you'll know that, right? Out here at the end, if we have a cross through it, it means it's a structural member, right? So that would be your rim joist. Yes, sir. Mm-hmm. Generally speaking, there's going to be some toenails along the way, right, to tie it in. But for the most part, the weight is resting directly, right? So for weight position, it's going to be just straight down. The other thing that typically will happen is whatever you're sheathing on the outside of the building, right, will carry down past this whole platform and tie into this as well. So that in combination, you're going to have a few toenails, not too many, right? You're going to have that in combination with sheathing that's going to come down over and nail through, right? And obviously nail into this, nail into the wall, and that's going to tie the whole thing together as well, right? So the thing about light wood frame is it's not like, you know, steel where we're welding pieces together. Most of it relies on this bears on this, which bears on this, which bears on this, right? So it just works its way down the structure, right? So there's not a lot of attachment that's really necessary, okay? When we get around a little bit further, we'll show you some other examples, right? Okay, so we move across here, right? This is our other edge condition, right? This is where our joists are running, right, perpendicular to our outside wall, right? They come across and rest nice and clean, right, on this sill plate, right? The anchor bolt goes through the sill plate, right? That obviously helps tie us down. Notice, in California, there's also a lot of hardware that's associated with these that ties it into the building system as well. We'll talk about those a little bit later on. There's a few examples of those, right? So in this case, we have our rim joist right here. That's on the outside. We have our sheathing across the top. We have our sill plate there with the anchor bolt, right? We come inside with these break points. This is where we're resting on an interior, right, load-bearing. In this case, it's a column that's supporting an I-beam underneath, okay? We wouldn't want to rest, right, these wood members directly on the I-beam because we have no physical way of attaching the wood to the I-beam, right? And so instead, we'll put this little wood strip, right, that's going to equalize the shrinkage with outside, right? Notice it matches, so it equalizes the shrinkage, right? And we can bolt that together and then nail into it there and there. This is also a piece of blocking, right, which you can see. Okay, so depending on the bearing condition, right? In this case, right, we have our I-beam. We've got our 2-inch block, right, to receive the toenails from either piece. That's doing the bulk of the support. It tells you in the book that the steel beams are usually 8 inches to 10 inches for residential scale, right? So they're not particularly huge, not like the ones we were seeing in the steel lecture. A little bit smaller scale, right? The other option is we can do a laminated wood beam instead, right, to support that weight. There's no difference in the drawing of a laminated wood beam versus a regular wood beam. In this age of construction, if you see a beam, assume it's some kind of a laminated or a LSL or an LVL or something like that. It's some kind of engineered lumber. And so we've got another example here, right? And we'll continue on, right? What happens if we don't want that beam to extend down into, we're worried about ceiling clearance, right? You don't have a full 8 feet. You don't want that beam sticking down a foot, 10 inches, or whatever, right? How can you go around it? We've got an example here where instead of resting on top of the I-beam, right, we've nested these underneath the I-beam, so the I-beam is actually recessed into the joists on either side. Notice we still have those wood blocks for the shrinkage, right? And it's being supported on the bottom flange, right? And then across the top, we're scabbing to connect the two pieces together to keep them, in line and consistent. We can do the same sort of thing here with a wood beam. This has two wood ledgers that are resting on it. It's basically the same concept, wood versus steel, right? And so then we move into the far more common way of doing it, right? And that would be, instead of making an actual beam, we'll take a bunch of the joists, right, and we'll sister them all together, and they'll work like a beam, right? So we're increasing the ability for those to hold. And what we'll use, and you've heard me refer to these earlier, is something called a joist hanger, right, which basically is a metal bracket that'll go around the joist and allow us to securely attach it, right, in line in the same plane, right, joist to beam, right? So we don't have anything resting on anything else, right? And then I'll show you. I have a picture of those in just a second. We can also do a lap joint, which is over there, which is just where we cross the two pieces, right? Another joist. Okay, so let's take a break. We'll come back. We're a little bit early for a break today. Come back in, say, 20 minutes, so 10 till 8. If I read that right. Yeah, 10 to 8. And we'll go from there. If you stay around and you want to come up here, we'll do test pass back, and you can look at your test.